That's ln. Yeah. Log natural log. We'll spend a unit on that. You don't necessarily need to know or love it yet. Don't worry, you will. But we're going to get some general shapes and look at how all of these play by the same rules when you want to move them around. Why would you want to move them around? Well, often we want to like match some data. So I have data that suggests that my business model looks like this. And there's like the law of diminishing returns. Like the more money I dump into research and development doesn't necessarily give me more profit. It kind of tapers off. And so I have data that looks like this. And so I want to use a log curve to describe it instead of like an exponential or a root graph. And modeling is one of the big parts of mathematics. Is like we want to make predictions, and if you can make the best prediction, you win the game. Okay, so these are just a handful of different functions that we use a lot in this course. There's other functions too. There's like logistic function does this. It starts kind of flat, pops up, and then tapers off again. That things like population growth does that, right? I know that sometimes population growth we model with an exponent, an exponential that just looks like it booms, but that happens up to a certain point and then it tapers off. So there are functions like that that are used elsewhere, but aren't necessarily near and dear to our course. Also, something that we'll use trig functions, sinusoids, like that. Yeah? But for now, these are kind of the basics, and this is roughly what they look like. So here's Desmos. This is y equals ax plus b, and you're not so surprised. It makes a line, and if you change a, it makes it steeper, right? And if you change b, it slides it up and down. Yeah, not a big deal. What you'll notice about a quadratic, we'll turn that one off. Quadratic makes a U shape, right? You're probably not surprised. The a term makes it kind of wider or narrower. And the C term slides it up and down. Oh, and the B term kind of messes with how it looks, like rocks it around here. These seem like they're doing different things, but really like all of the little mechanics of changing A's, B's, and C's do similar things to them. And we'll talk about what they do in transformations. I mean, that's what this whole unit's about. For now, we're just getting used to generally what they look like. If you throw in a cubic, it starts to look like that, right? And then as you mess with it a little bit, it changes its shape. Yeah. As you change B, it kind of slides it around. Exactly what it's doing, you don't necessarily need to know that this second, but just that as we mess with these coefficients, they change generally how they look. Oh, but D, this thing hanging out of the end, doesn't change its shape. It just slides it up and down. Right? So there's a cubic. It kind of looks like a parabola, looks like that. Cubic's just the same thing, but going down. So that's this one. Right? Exponential just is a boomer. Goes y equals anything you want to the x. Now notice like that looks different than this. This is x is the base and the 2 is the exponent. X is the base, the 3 is the exponent. The weird thing about exponential equations is you have a base that's constant and the x is the exponent. And so it kind of looks like that, right? And just comes up from there. Maybe you've seen those before. Logs look a little different, and we'll talk about what logs are. Log 2, or log x. It looks like that. Comes up, tapers off. And reciprocal functions look like y equals 1 over, 3 over, whatever, 1 over x. Cool. So maybe just roughly sketch a graph of these. That one's linear. Here, I'll type them in, I guess. This is ax plus b. This is a quadratic, so this is y equals x squared. This is a cubic, y equals x cubed. This is a exponential. Y equals, I don't know, 2 to the x. This is a reciprocal. Y equals 1 over x. This is a log graph. base 2 to the x. Kind of give a rough sketch, just so you see what they look like. P.S. Some of my notes are already in video format and up on the VLE. Some are not, like this section, and that's why I'm videoing. Like the video is not important, but it's taking this and all the sound. So if you're out for some reason, it'll be up on the VLE in this unit, right? So try not to swear too much. All right, I'll put this on the next page, but I'll give you a general sense of what we're up to. Now, generally, I want us to be able to take some basic equations and roughly be able to visualize them. Things like quadratics and cubics, and we'll get some more practice with like logs and exponents. But I want you to have a basic shape in your head of what each one of them look like, and then roughly as we mess with the values around them, the numbers in front or what we add to the end, roughly how it changes them. Some of them are so obnoxious that like, it's not worth our time to be able to try to think about it in your head, and we can graph them on your calculator. And so I want you comfortable with that too. But the pieces that we're interested in, as you graph something, like I don't know what this graph is. It looks like it's a cubic, so I bet it's like y equals, making stuff up, 3x cubed plus 2x squared plus 5, right? Like, I want you to be able to cite that this is probably a cubic just based on its shape. And once you have that, like I want, if we graph this, if we put this into the calculator, the pieces that are important when you sketch a graph are intercepts, x and y intercepts. Maxima and minima. This thing's called a local maximum. Because this, if you keep going this way, this is just gonna go up forever, right? So that's not the maximum of the whole function, because it just keeps going up on this side. But it is a maximum, it's an interesting point, right? It's a maximum within here, so we say that's a local maximum. Similarly, that's a local minimum, because this just goes down forever. So a local maximum, local minimum. Those are interesting points. If there's any like spot where the function doesn't exist, like a hole, like if you were in our last unit when we were saying like, oh, y equals, I don't know, 3 over x minus 2, or if you graph this, these two would cancel out effectively, but you'd see a little hole here. You can't have x be 2, and so you'd have a hole in your graph at 2, making stuff up that would look like that. And so if you notice that, you put up a little empty circle in there. So little holes, spots where the curve can't exist, and also asymptotes. Right, so here you have an asymptote right there. Can you spot that on the graph? Can you spot that in the function? Those are all important pieces. And when they say like sketch a graph, you just find those important pieces, dot them in, and then make a rough sketch. Yeah? If they say draw a graph, you need a printer, right? You need all the dots, or you need a lot of lead. You go, you make like 20 points and connect them really carefully. I will not ask you to draw ever. I want sketch, right? Bot, 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 4 or 5 points that are interesting, and then the curve. Neat. Okay, moving on. The good news of this is for many of these things, it's very calculator heavy. And so often you can just throw in a value into your calculator and it'll spit out a number for you. So grab your calculators and let's try one of these. Together, together, together. All right, so there's no reason you should know what that looks like, right? 2 to the x over x minus 2. That's too gnarly for us to like do in your brains. But I want you to make sure you can put it into your calculator. So go into y equals, clear out whatever garbage you got in there. And the fun part is typing in the equation and making sure it sits nicely. So this is 2 to the x. Take all that and divide by x. Close your parentheses, go minus 2. All right. 2 things that are messed up about this. What's one of them? Yeah, it's like it's not showing. It's only showing me a little piece of it because I was messing with the window in a different problem. What's up with all those dots? Do you have all those dots? No, I have stat plot on. So like sometimes you have weird things happening. That's from my statistics. So I'll show you how to turn those on later. That's what my seniors are doing right now. I'm gonna go to stat plot, turn them off, and then go back to graph. Okay, so there's the graph. I can't quite see exactly what it is. I usually try zoom 6, which is standard, which is 10 by 10 by 10 by 10, 10 by 10 by 10 by 10. And that looks better. It's a good place to start. Sometimes you can say zoom fit, and the calculator will try to guess what you want to see, but it's a calculator from 1972. It has no idea what you would want to see. Is that any better? No. So I might go back to zoom 6 and then try to manipulate a little bit. I don't need to see so much on the negative side. I don't need to see this so much. And I don't need to see quite so much of this. So I might change the window and say my minimum, I might just bring it down to like -3. And my y's, I might condense a little bit to like -8 and 8. Just see if that helps. A little bit, maybe less of this, right? And so it's a dance. It's a little bit of a dance, but it's all right. Change this to 5. Let's bring this back to like I don't know 7. Zoom, zoom. Okay. So I can tell there's an asymptote here. I can't quite see what's happening here, but I'm guessing it doesn't just go and kiss the x-axis once. It kind of looks like it dives underneath and then comes back up. So I'm going to zoom in on that in a second if I'm going to really graph this thing. But this looks like an asymptote. Doesn't look like there's any x intercepts or y intercepts. Oh, this is an asymptote too, right? So let's figure out what that asymptote is. You could just say trace, and your little spider pops up. You go da-da-da-da-da-da, and bring him sideways until he jumps over. I can tell he jumps over because my x became negative. And then as I go over, you can kind of see it plateau out and start approaching some value. What value do you think that is? What y value? Yeah, and if you're not sure, you could put in a y value. You could show me more y values. Oh, wrong way. Crank. What do we have? Show me more negative y values. Like that. Ah, I messed it up. says window range. I've got a negative backwards. So x min, x max, that's fine. Y min, so let's do -5. It's fussy. Very agreed. So now we can say trace. And as we keep moving it farther and farther back, you can see that it approaches -2. Right? There's other ways to do that. You can say second table, this in graph, and you can look backwards through here and so see what y values. If we go back on the x, you can see like the y value gets really, really close to 2, and eventually the calculator just gives up and is like, let's call it 2. So it looks like horizontal asymptote at 2. You can tell there's a vertical asymptote at 0 because there's an error there. So far with this, I would probably, if we were trying to graph this by hand, sketch it, we'd say, all right, I've got this asymptote at 2 there. I've got a vertical asymptote here. And probably the next things I need are those 2 intercepts. Okay, I kind of want to go right there. So you could zoom, and we could get rid of the scribble. We could zoom in. Bing. It'll zoom in on this little cursor. You see this pops up. And so you can kind of move him around, or her, could be a her, or they. Move them around until they're in the site that you want to zoom in on. Or you can do it manually with the window. Hit enter. 2 intercepts. Let's do it again just for fun. There they are. And then if you want to find those exactly, you can say second calculate. Calculate me at 0, please. Again, yes, annoying. But I think if you can drive your calculator, you'll be fine. All right, so there's my y. I'm looking at a positive y value. Now my y is below, so now that's the left and right bound. So 1 and 0. Yeah. And then you can calculate the other side similarly. How do I zoom in? Yeah, hit the zoom key and then. Oh, 2. Oh, that's super slick. That's super slick. I zoomed in by saying, I hit the zoom. I said in. So let me zoom out twice. So it was looking like that. I said zoom. Said in. And then I moved my little cursor around until it was where I wanted it, and I just hit enter.
Great, I'm in the middle of nowhere.
And then my cursor is still there, so you can just hit enter again. It's still kind of in the zoom mode, so you can just hit enter again and it'll zoom in more. Cool, so then those are our 2 points. This is an asymptote, so it's going to look like this, and and then from this side, it goes from positive to negative, so it must do this. And so that's all we need, right? We have an asymptote, we have an asymptote, we have an intercept, we have an intercept. It's good enough. Yeah? Nope.
Is there a way to, in the table, is there a way to like switch the x and the y? That I can see like if it was 1 over 2, for example, on the x, and it's just 1, 2, 3. If the intercept was at 1 over 2.
Yes, I see what you're saying. Switch like the intervals that you're seeing in the table. You can say in this table set. So Toby's asking about this table, I think, and seeing like when are these things happening? You can go into second table set and say where do you want to start the table and how much do you want to switch the table by each time. So let's go by like 0.5s, and then when you go to table, it's running by 0.5s. Some people really like the table. I find it's easier for me to visualize things with the graph, but run it how you like. Cool questions about that so far? All right. Bum, bum, bum. All right, so the second thing I want you to be able to do with your calculator is solve things by graphing. There's 2 ways to do that. And so we were trying to work with this thing and see what x value makes those both true. One way you could do this is like this is a function and this is a function. And one way you could do it is graph them. And so this is the red function, like that. And that's the black function. That's the hyperbola, or the hyperbola. And you can find where they intersect with your calculator. Let me show you that. And I'm sure you've already done that before. So let's quit that. Let's go y equals. Let's go 2 minus x in one of the sides and 1 over x in the other equation. And let's go zoom 6. So there's the line. There's that. That's this thing. Okay? And from there, we're trying to find an intersection. And so I might say zoom in and zoom in on the center of this just a little bit. And then we try to find the intersection by calculate and intersect. And all you need to do is kind of get close. It says first curve, it means I'm on the first line. Second curve means on the second line guess. So I just usually go click, click, click. Iterations. Good. I like that. I blew up my iterations. Now let's try it one more time. Calculate, intersect, and again, guess. Sweet. So sometimes if that doesn't work for you, there's a different method. I don't know why that's happening. There's a different method to solve that's sometimes more useful, and that's this. If you take, why am I drawing on this? If you take this and kick everything to one side. If we let's move everything to that side. If you subtract the 2 and then add the x, you've gotten, you've smooshed these two equations together. This should occur at 1, 1, it looks like. I think that's what's the case from here. Right? That at 1, 1, the red line and the black line are in the same spot. So my guess is our solution should be 1, 1 if my first technique worked. Obviously something happened, or maybe there's a reason you can't solve it that way. Another way is to smush all of this into one equation. And if we graph this is kind of a hybrid. I'm going to get rid of these two for a second. You can if you don't want to delete things, you can just turn them off like that. I'm going to put in this hybrid that I made. Nice do. Plus x. If we graph that thing, it looks really different. But I want to know, when does that thing equal 0? That should be the same solution as when this side and this side are equal. And sometimes that's easier to find. When you say calculate a 0, where does that happen? Left bound, I don't know, negative. Yeah, just go 0.1. Right bound, 5.
It's only going to give you the x coordinate.
Yes, and that's okay. So this, yes, that's sure. Oh, and it said 0.9999999. Right. So if we did that again, left bound, right bound, guess. So that's its way of saying 1. Right? So it said my x value is 1, but that's all we really want for this, is solve for x. Well, I want to know where they intersect. They intersect at 1. What value are they at that point? They're both 1, but that's not the solution. The solution is what x value can I put in to make that side equal to that side? What x value can I put in here to make this equal to 0? They're both of them. So 2 different ways. Which way is better? If that's the art form of it. Cool. Questions about that? Aight. Then there's a handful of problems in your fancy new packet, which I'm chucking out to you now.
Actually, it's 32.
The first page is just about can you graph things using a calculator and replicate it faithfully on paper. So try that out.
Oh my goodness. What?
Love it. Thank you. Oh, it is Wednesday. Wednesday is a good day.
Oh, yeah, I was thinking.
Beauty. Thank you.
Massive.
Thank you.
But I was like, oh, it's like, it was like, yeah, I gave her it's to do, I have a spiral review.
Beauty. Thank you. Ooh, and a sticky note.
Because it went really well, so I had to redo it like 5 times.
Good. Thanks,
That was
Ed.
weird though, but it
Perfect.
contributed to it really cool.
Tiny. Very efficient. Thank you. Yeah, let me show you the first section, just so you can kind of get a roll on it. So, practice packet.
Use technology.
Use technology. I like that. Oh, that's function. That's
function.
function.
This is my old one that I.
Oh, beauty.
Sorry, I didn't do on it.
So endearing. Transforms. All right, so this is the same thing as your second one. So why don't we just cut to the chase and jump to this one? It says graphene.
Will we finish this unit before the holidays?
Yeah. Yeah.
All of this?
Yeah. Hey, a lot of that is solutions because like they have to give you a picture of what you should be getting. So like the 3 pages of that is just solutions for this. So let's start with this page and not like the first page you see. So they're both the same, but I like this a little bit better. All this is asking you to do is take this equation, throw it in your calculator, find intercepts. Turning points are like interesting squiggles. Asymptotes, tell me the domain and range, and just give me a sketch of it. Right, so this should look like it's a cubic. I can tell because there's 3 x's, so it's going to look something like that. Anywhere you want. Put it in your notebook. You could do it in there if you want. But yeah, there's scrap paper in the back if you want to steal some of mine. So that's what that first part is. Can you sketch it? Would it be helpful to have graphs in there next time?